All right, let's dive in. Today, we're going to talk about a vulnerability that is so sneaky, but incredibly powerful. It can turn a simple command, something that just prints text to your screen, into a master key that unlocks an entire system. We're talking about the format string vulnerability, and you're about to see how a single line of text can become a weapon.
I mean, it sounds like something out of a movie, right? A simple, everyday tool that gets turned into this powerful weapon. But nope, this isn't fiction, this is real. And the answer to how it's even possible, well, it's both brilliantly simple and, honestly, kind of scary. Let's break it down.
So, where does this all start? Well, it begins with a function that pretty much every C programmer learns on day one, printf. Its whole job is just to print formatted text. But hidden right there in its simplicity is a critical detail that can be completely exploited.
Okay, so the entire vulnerability, the whole thing, comes down to a difference that is so tiny you could blink and miss it. On the left, that's the safe way to print whatever a user types in. On the right, that's the dangerous way. The only difference is where the user's input goes, and that one tiny change, well, it makes all the difference. So what exactly is a format string? Think of it like a template for your text, but the real magic, the secret sauce, is in these little things called format specifiers, like %x or %s. They're not just placeholders, they're actually commands. They tell printf to go fetch a piece of data and show it in a specific way, and that's where the power lies.
So what happens when an attacker gets their hands on this template? Well, their first move isn't to crash the program. Oh no, it's to get the program to talk, to spill its guts, really. They can literally reach into the application's memory and just start pulling out secrets, one piece at a time.
And this is where the clever part comes in. What if an attacker's input is just a string full of these specifiers, like %x, 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 but they don't give it any variables to fill those spots? You'd think, okay, the program's just going to crash, right? But nope, something way more interesting happens.
So yeah, instead of just giving up and crashing, printf does something weird. It goes looking for those missing variables on something called the stack. You can think of the stack as the program's short-term memory. And when it doesn't find the variables it expects, it doesn't stop. It just keeps reading whatever happens to be there next.
And what does it find? Well, take a look. As printf just keeps on reading down that stack, it basically stumbles upon a treasure trove of information. We're talking variable values, memory addresses, and most importantly, these things called return addresses, which are like breadcrumbs telling the program where to go next. All of this stuff is supposed to be private, but now it's all out in the open.
So, just by feeding the program a simple string of X's, an attacker gets a raw dump of the program's memory. They're literally taking a stroll through the stack, piece by piece, just looking for anything valuable. But reading data? That's just the beginning.
Okay, so reading memory is one thing. That's a huge problem. But it's just the start of the story. The real catastrophic danger comes when the attacker figures out how to not just look, but to write. This is where things get really serious. We're moving from just eavesdropping to actually taking over.
I want you to meet the star of our show, the N specifier. You almost never see this one used in normal code, and for a very good reason. Unlike all the other specifiers, it doesn't print anything, it writes. It takes the number of characters that have been printed so far, and it writes that number to a memory address. This little guy? This is our weapon.
So, you might be asking, how does an attacker control what gets written? It's actually a clever trick. It's all about controlling how many characters get printed before the %n shows up. They use a feature called padding to say print exactly 100 characters. Then they stick %n at the end and boom, the number 100 gets written to any memory address they want. It's like setting a counter and then saving the final tally wherever you choose.
And this, right here, is the huge shift. Reading memory lets an attacker learn about your system, but writing to memory lets them change your system. Now they can mess with variables, corrupt data, and most importantly, hijack the entire program.
Okay, so now we have this incredible power. We can write a small number anywhere we want in memory. So what's the endgame? What's the ultimate target? It's all about seizing control of what the program does next.
Well, a perfect target, the bullseye, is something called the Global Offset Table, or GOT for short. The absolute best way to think about it is like the program's address book. When the program wants to do something common, like call the exit function, it looks up the address for exit in the GOT. And here's the crucial part. That address book is writable.
The plan itself is actually pretty straightforward, but the result? Absolutely devastating.
an attacker first gets their own malicious code, we call it shellcode, into the program's memory somehow. Then, using our trusty %n specifier, they overwrite the address for a normal function, like exit, and replace it with the address of their shellcode. So what happens? The program thinks it's about to exit, but instead it jumps right into the attacker's code, giving them total control.
All right, it's time to put all the pieces together. Let's look at the anatomy of this perfect heist, the final, masterfully crafted exploit string that does everything at once.
Okay, step 1. The attacker has to get their malicious code into the program's memory. A really common way to do this is to hide it in something called an environment variable, which is just data that's available to programs running on the system. Once that shellcode is sitting in memory, they just need its address and the address of their target in the GOT. Then they're ready to build the final payload.
But wait, there's one more clever little trick here. Writing a big 4-byte memory address all at once can be tricky and messy. So instead, attackers often use a variation called %hn. This lets them write just 2 bytes at a time. It gives them surgical precision, allowing them to overwrite the first half of the address and then the second half nice and clean.
So when you look at the final exploit string, honestly, it's kind of like a work of art. It's not just a jumble of characters. It's a tiny program in itself, containing the addresses it needs to overwrite, the precise pad and calculations to create the exact values it needs, and the %hn commands to perform the final writes.
And this is basically what it looks like. It's this beautiful, terrible structure. The target addresses are put right at the beginning of the string. Then, later on, the %hn commands use a special syntax to say, hey, go grab that address from the beginning of the string and write to it. The whole thing is like a self-contained missile ready to launch, all packed into one line of text.
And here's the kicker, the most mind-blowing part of this whole thing. After all that setup, all that cleverness, it takes just one single malicious string passed to one vulnerable printf function to go from a simple text input to complete and total control of a machine.
You know, this whole format string vulnerability is a huge wake-up call. It's a stark reminder that even the most basic, fundamental building blocks that we use to build our digital world can have these hidden, incredibly dangerous flaws. It really makes you wonder, doesn't it? What other harmless functions are we all trusting every single day? And what secrets might they be hiding?